Hi guys, we were discussing about magnetic effects of current. So we learned that a current carrying conductor produces magnetic field. So it's a powerful statement. Magnetic field source other than the natural magnet, a current carrying conductor. So this was understood with the help of Oersted experiments. So we tried to figure it out the direction of the magnetic field, and we have some experimental evidence. The iron filings, they form around a current carrying conductor a concentric circles, and we tried to figure it out what is the mathematical expression for a current carrying conductor. Suppose this is a current carrying element, an infinite wire. So we tried to find the magnetic field at a point B through this current carrying conductor. Then we got an expression by using Biot-Savart's law. So this Biot-Savart's law says about the magnitude of the magnetic field due to a current carrying conductor. So according to this law, the magnetic field due to a current element dl carrying current I at a point P, which is at a distance r, is given by dB equal to the small magnetic field equal to mu naught upon 4 pi times I dl sine theta upon r square. So here dl is the elemental length. So this is the smallest portion in the current carrying conducting wire. So due to this smallest portion, the smallest element of the magnetic field at point P, to figure it out, so this is the expression dB equal to mu naught ideal sine theta upon by 4 pi r square. To find the direction, here we used right hand corkscrew rule. It means if the dl is rotating about position vector r, then the right hand corkscrew rule says that the alignment of the magnetic field, which will be inside or outside. So in this case, the magnetic field is moving into the page, or we can find this by using a right hand thumb rule. So the right hand thumb rule says that if you hold a current carrying conductor with your right hand, the curl of fingers indicates the direction of the magnetic field around the current carrying conductor, and the thumb indicates the direction of current. So with your right hand, if you can switch towards to the direction of current into your thumb, the curl of fingers gives the direction of magnetic field. So later I applied to find the magnetic field using Biot-Savart's law to a current carrying loop. So this we got an expression to current carrying loop, the magnetic field due to a current carrying loop. You can write that expression as the magnetic field at the center of the loop. We can write that B equal to mu naught I upon 2r. So here r is the radius of the loop and I is the amount of the current which is flowing in the wire. So this we derived by using Biot-Savart's law, and later we applied the same case to a current carrying conducting loop, but the position of the magnetic field along its axis. So the position of the magnetic field along its axis, we got an expression B equal to mu naught I upon P equal to mu naught I a square upon 2 times r square plus a square whole power 3 by 2. So that gives the magnitude of the magnetic field due to a current carrying loop at a point P, but that point is along the axis of the loop. And to find the direction, so to find the direction, either we can use same the right hand thumb rule. By using right hand thumb rule, we figure it out the direction of the magnetic field. So here the direction of the magnetic field I can show. So this is about the direction of the magnetic field. Same, the curl of fingers shows the magnetic field direction of our right hand. The thumb indicates that the direction of current. So far this much we covered by using Biot-Savart's law. But Biot-Savart's law having its own limitations. Suppose if I want to find the magnitude of the magnetic field in this case, the total magnitude. So here I got a small element of the magnitude of the magnetic field. So to get the total magnetic field at that particular point, so what shall I do? I need to do the integration. So we need to do the integration on both sides. So if you do the integration on both sides, that leads a tedious mathematics. So we are going to find an alternative law which simply explains about the magnetic field due to current carrying element, and with the help of that law is it easy to identify or easy to calculate the magnitude of magnetic field. So in this class we are going to concentrate about an alternative law to find the magnitude of magnetic field due to current carrying elements. Maybe it's a straight wire or some other. So we will get a very important, very useful law which is known as Ampere's Circuital Law. So Ampere's Circuital Law is very handy to find the magnitude of magnetic field due to a current carrying element. So this law says about, this law states that the line integral of the magnetic field around any closed circuit equal to mu naught times the current I threading or passing through this closed circuit. In mathematically, closed integral B bar dot dl equal to mu naught I. Here B bar is magnetic field vector and dl is also an elemental length vector. So the dot product of two vector, we get that B dl cos theta which is equal to mu naught I. So here I need this formula, the closed integral, it's a closed integral B bar dot dl bar is equal to mu naught I. So let us try to find what this term says. So here my task is that I would like to find magnetic field. Suppose I am having an infinite length of wire which is carrying current I. So I would like to find magnetic field at this point. I wish I would like to find magnetic field at this point P. And I was trying to find very easily because Biot-Savart's law gives a very tedious mathematical expressions to find the integrations. Since we are having that formula, but we can do that, but that leads to a tedious mathematics. But here we are trying to find an alternative, which thinks an easy way and which makes to do the calculations very easy. So for that, Ampere circuit law says, which is given by Ampere, first we need to bring an Ampere loop. The Ampere says that, yeah, you bring something like this loop. It's just like a honeybee catching net or a fishing net. So this net, this loop here I highlight, and this loop is having a name known as Amperian loop with the help of that. So what is this loop? Let me talk 2 minutes about this. And first of all, this loop we known as a open loop. It's a loop, it's a closed surface, and it's having its boundary, means this is, so this is the boundary, and it is having particular shape also. Yeah, this is made up of a circle, so that's why it is shaped like that. Suppose if you made up of a square, maybe that shape is like that. But if you can add a net which is backside to catch that, so this is also becomes an Ampere loop. Oh, I made it. So this Ampere loop will be any shape, but it should be closed. And now what shall I do to find the magnetic field? I attach this Ampere loop to my current carrying conductor. So I consider a circular Ampere loop. Now this circular Ampere loop I highlight with that, and it should be closed so that I can attach through it. So what happens in this case? My current carrying element is punching the Ampere loop. That should be done. So in this current, you should mention that current enclosed. Current enclosed the loop. Now, okay. Now we have taken Ampere loop. That Ampere loop I attach to the current carrying element. Now after that, what shall we do? Now to find the magnetic field at a point P, so it means I need to take this loop at till that point. So it means I need to extend this loop. So if we extend this loop till that point, yeah, we get it something like that. Now this time I will change the shape of the Ampere loop. Now it happens something like this. Yeah, since the area has increased. Now this loop is having a radius of r, the Ampere loop radius at a point. It should be at center, but you try to adjust with that. It means this net is having a radius of some particular, then only we can easily to calculate that area of that boundary. So in this one, this thing is a boundary. Okay, now first step what we did, we have taken the current carrying element, and second step we consider an Ampere loop. That Ampere loop is a closed loop, just like a polythene bag. If you can just keep the polythene bag on that current carrying element, and that polythene bag is having certain boundary, and our current carrying conductor should enclose the loop. If it is not enclosing, so it's useless case. Now, what shall we have to do? Now, if you observe in this formula very carefully, so I is the current which is enclosed. It means I already having this one. And B, which is something I am going to find out. Yeah, B bar is magnetic field which is I am going to find out. That is my final task. Now here we need to figure it out. One more thing, mu naught, it's a constant. Yeah, it's having already its own value, that is 4 pi times 10 power minus 7. It's not a big deal. Now who is this? dl bar. And where is this has to be taken? So this dl bar is something is different what we consider in the Biot-Savart's law. In the Biot-Savart's law, we consider the dl bar on the current carrying element itself. It means I have considered a small elemental length dl from the current carrying element in the Biot-Savart's law. But right now, so this elemental length dl we should not consider on the current carrying element. Now, if you walk on the boundary of the Amperian loop, just you walk on the boundary of the Amperian loop and you cut each a small elemental length dl. So this is a small elemental length dl. Suppose if I take a small elemental length dl at P, yeah, this much portion is small elemental length dl in the boundary of the Amperian loop. Okay, if it is a difficult to pronounce, you can just call it as an Ampere loop, not a big deal. So everything is at here. In the net I am drawing. So in my honeybee net, I need to consider a small Amperian loop. Okay, now I got it. Now to find the total magnetic field. Now in this formula what shall I do? So closed integral B bar dot dl equal to mu naught I, current which is enclosed. Now B bar is non-integrable terms. I need to do the closed integral B bar closed integral dl. So dl is also a vector equal to mu naught I. Now B bar, now closed integral of dl. It means what is this loop area? The loop is a circle. The circle having a radius of r. The loop area becomes 2 pi r, which equal to mu naught times I. Now the magnitude of the magnetic field B equal to mu naught I upon 2 pi r. See here I directly got the magnitude expression, which is V bar equal to mu naught I upon 2 pi r. Within 3 steps, I am able to find the magnitude of the magnetic field by using Ampere's law to a current carrying conductor. But with this limited mathematics easy way, if I try to find by using Biot-Savart's law to find the magnitude of the magnetic field in this case, so it is very difficult, we cannot get that. So because here we need to convert so many things in terms of that radius, it's very difficult to apply Biot-Savart's law to calculate the magnitude of the magnetic field in this case. But Ampere's law is very handy. It's very easy to find the magnitude of the magnetic field for a given current carrying conductor. Now, let me ask a question. Is it necessary to take this loop as a regular shape? Since I have taken this loop as a circular boundary, I have taken an Ampere loop, a closed loop. Now this is a boundary, and I have taken this loop off like this, just like a polythene bag having an open surface. So I inserted a current carrying element. Now this current carrying element is punching the bag. Now Ampere loop should enclose the current. Yeah, in this case the Ampere loop is enclosing the current. So instead of taking this regular shape, so what happens if I consider a irregular crooked path? Yeah, this is also a closed loop. Now this is also having a boundary. Now if I can attach a polythene bag backside, yeah, it is also having a closed surface. Shall Ampere's law works at here? Yeah, obviously it works. But is that formula, is everything is same? Yeah, it's everything is same. There is nothing to change. Until unless if you know a very good integration to find the total length of this crooked shape which I consider. So this is the shape which I consider, which is irregular. So in English that is called as crooked. Until unless if you know very good integration techniques to find the area of that irregular loop which you consider, then you can get the same result. Obviously here also you can get the same result. But the regular shape, just like circle, square, which we know the areas. So this area find out is very easy. If you know the radius r, its area goes to 2 pi r. And later if we can take any another regular shape, suppose if you take a square or rectangle, it's easy to find these regular areas because the formulas will help us a lot at here. So there are the certain situations where Ampere's law only gives very easy way to find the magnetic field. And similarly, there are the certain situations to give easy way to find by using Biot-Savart's law. So this is all about Ampere's law. So the Ampere's law is very handy and it's a substitute. It's a substitute to find the magnitude of the magnetic field due to a current carrying element. So what is important concept at here? It is all about by considering an Amperean loop. So Ambient loop is a closed loop. It should have some irregular shape boundary. It's better to take, it should have a regular shape boundary. And that it should be closed. So depends upon the situation, we can consider this kind of a regular shape and it is having a closed surface. Just like always you imagine to find the magnitude of a magnetic field to a given conductor, you better to carry a transparent hat. A hat should be fixed on your head, depends upon the circumference or the area of your head, but that hat should be transparent. Then only the current through punch it, current should enclose it. So to given any case, we can use this one and only formula, the closed integral of b bar dot dl equal to mu naught I. Yeah, two things here I need to explain. So whenever we consider this loop, the elemental length dl. So here the elemental length dl is a smallest portion in the loop. Don't forget that. It is the smallest portion in the Amperean loop, what we consider. This is the smallest portion in the Amperean loop. not in the current carrying element. We take that dl in the current carrying element in the Biot-Savart's law, not in the Ampere's law. That one small change again I am frequently saying. Fix it in back of your head. And so here, to this Amperian loop, what could be the direction of the magnetic field? The magnetic field to this Amperian loop always in tangent direction. So if I consider small elemental length at here, so the angle between magnetic field and the elemental length, this angle goes to 0. That's why this formula we rewrite as closed integral of b bar dot dl, the dot product of two vectors. What we can get? B dl cos theta. Yeah, the dot product of two vectors equal to cos theta. Here the angle between the elemental length dl and magnetic field, they both are in the same direction. So if they both are in the same direction, the angle between them goes to theta equal to 0. So theta equal to 0. Wherever you take, always the magnetic field is tangent to the Amperian loop. The magnetic field B bar is always tangent. That's why the magnetic field here we can call tangential magnetic field. It should be tangential to the Amperian loop. Yeah, it always happens. So then we can easily apply this Ampere's law to close integral of b bar dot dl equal to mu naught I. So the proof of the Ampere law is proved for this current carrying conductor. So if you do the same by using Biot-Savart's law, we can end up with the same result. So the Ampere's law is very helpful and handy to find out the magnitude of the magnetic field. Coming to the direction, to find out the direction, we were using the same, the right hand thumb rule. So hold the current carrying conductor with your right hand. So the thumb indicates the direction of current and the curl of fingers. The curl of fingers indicates the direction of magnetic field. For a circular coil, so this is the resultant magnitude of the magnetic field direction. So this is how we apply Ampere's law in supplementary to the Biot-Savart's law. Let us try for one small example. What is the importance of the current enclosed in the Ampere's circuital law? Let's try to apply the Amperian circuital law for given case. So here there are 4 wires are there. Through these 4 wires, so I enclosed a circular Amperian loop. So the currents are punching the loop. So here you can see the holes. So let's try to apply the Ampere's law. The closed integral of b bar dot dl equal to mu naught I. So here I is current enclosed. Now I got a doubt. What is the total current passing in this given situation? So what is the net current? What is the net current which is in this present situations? To calculate the current enclosed, see the direction. How many currents are moving up and how many currents are moving down in the Amperian loop? Suppose if I can make the Amperian loop as visible, so at here you can see the boundary. So this is the Amperian loop. So through this loop the currents are punching and going. So it's now try to recognize with the help of arrow marks how many currents are going up? The current net equal to currents which are moving up plus currents which are moving down. Now if we can write currents which are moving up, so let's find the arrow marks which are going up. Yeah, these two arrow marks which I am going to highlight with yellow, so 3 amperes and 4 amperes. So these two currents are the which are coming from the down to up. So currents which are coming up at here, 3 ampere plus 4 ampere, which gives me 7 amp, plus currents which are going down. So going down, so here the 5 ampere current is there and here 2 ampere current is there. So the total current goes to again 7 amp. So what is the current net? So currents which are coming down, if I can take the negative sign, so that net current goes to 0. If the net current goes to 0, what is the total magnetic field which is contributing in this situation? Integral closed integral b bar dot dl equal to mu naught I. Here I value equal to 0. Therefore closed integral of b bar dot dl equal to 0. So in this situation there is no magnetic field because the total currents enclosed by the given conducting wires are equal to 0. I hope you are getting some meaning. Let us try to another situation. Apply the same Ampere's law to this given situation. Now first we need to look at how many currents are enclosing. Sometimes some currents are not enclosed within the loop what we consider. For that we need to highlight the boundary. So if I like to highlight the boundary with this green color, so how many currents are punching through this enclosed surface? So here I am seeing 3 holes in the Amperian loop. Yeah. So in these 3 holes, the current conducting wires are which are coming out from the down to top. Yeah, let it be. Now I can apply closed integral of b bar dot dl equal to mu naught times I. I always used to like to write enclosed. It's very handy to remember. So this is something called as stick to basics. Please stick always to the basics. Then things will be very easy to find out. Now let me find out what is the total net current. So in this case also I will find what is the currents up and which are the currents are going down. And upward current is one and all I can see, that is 3 amperes, 3 amp, and currents which are the coming down which equal to, which is 7 plus 5. Yeah, 7 plus 5, the total current goes to here the 12. So the current net, so the current net here I supposed to take difference because current value should not be negative. We need to calculate the total net, whether it is comes always in positive only. So the difference value at here, so this is the symbol of difference, please mind it. So the net amount of current, if you can take 12 minus 3, here I can get 9 amp. Now let's substitute in that formula the closed integral of b bar dot dl which equal to mu naught I. So here mu naught value 4 pi times 10 power minus 7 times current 9 amp. So the closed integral of b bar dot dl which equal to, so we can do the rest of the calculations how much it comes. So that will becomes the value of the magnetic field through this element. Here I am not going to find the magnitude of the magnetic field, so that we will solve for a given special particular condition. This is only for I am discussing about to know how to apply Amperian laws to the given loop. Now try to apply in this case. This is the final example. So first I need to mind about where is my Amperian loop. Yeah, even in this case 3 conductors are given, but one conductor is only covering the Amperian loop. So one and only current is punching through the Amperian loop, which consider at here. So what about the others? Is it need to consider to that? No, we cannot consider, because those conductors are not in the Amperian loop. They are on the out. Now what is the magnetic field due to this current carrying conductor? We can apply the same formula, closed integral of B bar dot dl equal to mu naught I. Here the current I equal to just 2 amp. So we can find closed integral of B bar dot dl bar is equal to mu naught times 2. We can substitute, that is 4 pi times 10 power minus 7 times 2, which gives 8 pi times 10 power minus 7. So this is the magnitude of the magnetic field. So after this we can find the closed integral, the area of this closed integral. Suppose in this case, instead of this loop, if I consider a circular, so this value will be turned out very easily, because we know circular radius, easily we can find it out. So this is the way we can apply Amperian Circuital Law instead of Biot-Savart's law. And again I am telling where the Biot-Savart's law can be used very easy, and where the Ampere's law you can use. Biot-Savart's law is very easy to use for a circular loop. And Ampere law to circular loop is very difficult. To the circular loop it is difficult. We do not use the Ampere law. And in the rest of all the cases, so for straight conducting wire we can use the Ampere's law, and infinite wire, infinite long conducting wire, we can use Ampere's law. Not only that, in the coming classes we can call magnetic systems, that is called as solenoid. Very easy to use Ampere's law into a solenoid, and a toroid. So these two are the some magnetic systems, I can say. I can talk about that in the coming classes. They are the very necessary in the electrical components. So to that electrical components of in a given circuit, so these play very important role to generate magnetic field in an electrical circuits. So to find the magnitude of the magnetic field for a given solenoid or toroid or straight wire or infinite long wire, so this Ampere law is very handy to use it. But to this all the cases, Biot-Savart's law is very difficult, very tedious mathematics we need to do. But Biot-Savart's law is helpful to find out the magnitude of the magnetic field through a circular loop. But to this case, the Ampere's law will becomes a little tedious. So that's why these two are having its own importance.